A very good evening. I greet to Sir Halim and to my fellow friends. Today, I will represent my seismic data processing technical data review. First of all, I'm going to introduce myself. My name is Isaac and Andria with ID number 16002521. So I'm going to review presentation today for the chapter of deep move out. First of all, we will go through the table of content, which gonna encompass introduction, background of study, problem statement, analysis content, and conclusions and recommendations. First of all, for the introduction, the main objective of the deep move out is that it is for the zero offset migration, which will be turned to mapping the non-zero offset data to zero offset section. So therefore, this DMO or deep move out correction need to be applied after NMO correction or normal move out correction, which is on the pre-state data. The reason they need to be applied is that it is to preserve the conflicting dips that will occur during the zero offset migration. And this chapter will give more closer representations of the zero offset section compared to the conventional common midpoint that we do for the zero offset section. So for the NMO or normal move out plus deep DMO or deep move out and the plus post-state migration will provide an alternative to pre-state migration. So moving on to background of study, we have two pictures here, which is the CMP or common midpoint is vertically above CRP with a flat reflector. And the other guy is that with dipping reflector, there was no longer common and non-vertically below midpoints. So on the right side, why it's more better is that the conventional stack will be ignores reflection point that spread out. And the event that on trace with the CMP will surface but with different subsurface reflection points. This eventually leads to the smearing of the deep reflection events from what we can see from the second picture of the dipping reflector. So for deep vs velocity, from the figure, we can see that for the uncorrected CMP gather, there was difference occur between geological dip with the geological dip, and the other one is no geological dip. So this one is the one that with the uncorrected, and the other one is the corrected CMP gather, which is using the velocity or V. This flat layer model for the NMO velocity is too slow for a dipping horizons. That's why the NMO will be overcorrect the dipping horizon from what you can see in the second graph. And for the second picture, the dipping reflector appears to be faster and the apex may not be centered. The stacking velocity, which will be applied during the dip correction, dip move out to correction is usually the dip independent. And only one event, because of that, only one event can be properly stacked. Okay. For the second picture, we will have the dipping reflector with an azimuth, and the other one is dipping reflector with velocity. So the formula is most or less the same, but there was a difference in the angle, which is for azimuth, we have cos alpha, and the other one is cos angle, or from what you can see from the dipping reflector with azimuth and the deep reflector with velocity. So for how we gonna get for the cos alpha is that or apparent dip is that from equal to sine angle multiplied by cos tangent. Okay. Moving on. So the problem statement for today is that for this topic is that each stress in a common cell gather will have to be deep move out corrected using a different move-out velocity. To do that, we need to use pre-stack migration and deep move-out correction to get the new data. The DMO process will correct the move-out velocity of a dipping reflector for the true dip angle and yields a dip independent move-out velocity at the unmigrated position of the dipping reflector. So from this phrase, we can see that if we use the unmigrated position of the dipping reflector, it will be very hard for us to find the true dip angle. So that's why we need to do the DMO correction. The apparent dip is equal to the true dip when the source receiver azimuth coincides or coincidental with the direction of the dip line. The common cell gather does not coincide with a common midpoint or CMP gather, which will cause non-uniform spatial sampling of the data output that will be get usually from the Python. And for analysis content, we have NMO equation for a horizontal reflector, which is the T power of 2 equal to T power of 2 plus X power of 2 over V over 2. X, from what you can see from the graph, X is the distance and the V is the velocity. And for the second part is NMO equation for a dipping reflector, where we have two parts, which is NMO part or normal move-out part and DMO part. So to get the NMO equation for the dipping reflector, the both of these equation must be minus for each other. And this figure, for the first one, is that energy can be moved in two steps from the source to receiver, which are the NMO and DMO. So that's why we will get this equation, which is the TD or TN equal to TN to the square root of T square minus 4x square over 4 N over V NMO square. And the other one is the NMO, which has been applied in CMP for the increasing CMP, and the other one is NMO, which have been applied in the offset. Moving on, the DMO will move or the energy to a different surface in the midpoint location from what we can see in the graph or the picture. The zero offset position is the actual of the reflection point. So the migration that we will be done after we get the data is we'll move the energy to its true time distant location. So before we interpret or analyze the content, we must do migration or for post migration. The zero offset trace will be done in a post-state migration after doing the deep move-out correction. So there was some process that we must do, which is the NMO, and then after that DMO, and after that is the zero of post-stack migration. After DMO, events in the midpoint gather will reflect from the same point, which are CDP or center depth point. After doing DMO and NMO correction, all traces will be zero offset. So we can say that we can exclude the one that we didn't need, and we can observe the one that we truly need from what we can see from our next example. Okay, and this one is the DMO amplitude calculation, where there was move out update, the half source receiver offset, the depth to reflector at the midpoint, which is along the normal line, and the last one is the reflector local dip for the calculation part. And this one is the example of the unmigrated section without DMO and with DMO, where we can see a more clear figure of the DMO migration part, and we can interpret and analyze the seismic section that have been done here, and we can observe more clearly better than the one that without DMO. And the next example is the one that have been done with migrated section, where there are less error and with clear graphic information, and we can also see that there was a true angle of dip. So that's why that is one of the advantages of migrated section, where we can exclude the one that we didn't need and and remove the one that we didn't need, and we can get the one that we only need or only need to be interpreted. And the next example is the data that the one that without DMO and with DMO, where we can see clearly that more unnecessary information will be removed out, and we can also more clearly can see that more accurate data that we can get from the seismic session. For conclusions, the DMO is the pre-stack partial migrations. The properties, there are three properties of DMO, which is as it decrease, it also the depth also increase. And the other one, the second one is it will be increased as the offset increase. And the third one is the DMO increase as the depth increase. And for the will migrate offset trace into their zero offset trace locations. And DMO also generates surface midpoint gathers which be containing zero offset trace after post-stack migration. And the advantages of DMO also is that if there was a multiples that exists, it is necessary to use a careful approach where we can remove the multiples before the DMO process. And the advantages of other DMO is that it is to use for eliminate travel path disparities and remove the velocity contention where we can see in the previous example. So for the recombination part is that we can start with the DMO where it will start with the pre-stack data and apply the normal move-out correction or NMO using a deep independent velocity to get the DMO correction. And the second part is that sort the data from the move-out correction CMP guiders to common offset section. This one we can use in the Python. And the third one is that we're going to perform Fourier transform of each common offset section in midpoint to reduce the error. And the fourth is for each output frequency that we apply, we can use the phase shift exponential sum for the resulting output over input time. And the last one is that we can use the perform 2D inverse Fourier in our DMO correction data. So that's all for my presentation today for technical review presentations. Thank you for listening, and that's all from me. Thank you very much.